Our reality is a brilliant, convincing illusion. You and I experience a world of 3 spatial dimensions and a single flowing dimension of time. This is the stage upon which our entire lives play out. Yet what if this stage is merely the visible fraction of a far grander structure? This is not a question for science fiction, but for the most advanced frontiers of physics. For over a century, theoretical physicists and cosmologists have been forced to propose that our universe possesses hidden dimensions. These are serious mathematical frameworks designed to solve the most profound mysteries in existence, from the bizarre rules of quantum gravity to the enigmatic force of dark energy. By the end of this journey, you will have explored 30 distinct theories that each propose a radically different blueprint for the cosmos. We will see how entire universes could exist on membranes, how gravity might be leaking into unseen realms, and how our 3-dimensional reality could be nothing more than a holographic projection. What does it mean if the very fabric of space and time is not fundamental, but emerges from something deeper and more strange? This exploration begins with a single, elegant idea from a century ago, a theory that dared to add a 5th dimension to reality. In the 1920s, a physicist named Theodore Kaluza wrote a letter to Albert Einstein that would quietly change everything. Kaluza performed a remarkable piece of mathematical magic. He took Einstein's own equations of general relativity, which perfectly describe gravity as the curvature of our 4-dimensional spacetime, and he wrote them out for a universe with 1 extra spatial dimension. The result was astonishing. From the geometry of this 5-dimensional world, Einstein's equations for gravity emerged naturally, but so did another, completely separate set of equations. They were the very equations that James Clerk Maxwell had derived decades earlier to describe the electromagnetic force, the force behind light, electricity, and magnetism. In one elegant stroke, Kaluza had seemingly unified the 2 known forces of nature by simply adding more space. There was an obvious and enormous problem, of course. Where is this 5th dimension? We do not see it. The solution came from another physicist, Oscar Klein. He proposed that this extra dimension was not like the vast, expansive ones we move through. Instead, it was curled up on itself, compactified into a loop so incredibly tiny that it exists at a scale far, far smaller than a single atom. Imagine a garden hose stretching to the horizon. From a great distance, it looks like a simple 1-dimensional line, but up close you see its circular surface, a 2nd dimension curled into a tiny cylinder. Klein suggested our entire universe might be like that hose, with a microscopic, circular 5th dimension wound around every single point in space. We are simply too large to perceive its endless, tight curvature. This was the birth of the Kaluza-Klein theory, the pioneering idea that launched the entire modern pursuit of hidden dimensions. It was a breathtaking vision, suggesting that the fundamental forces we experience are just shadows cast by the geometry of a higher dimensional reality. For a moment, it seemed physics had found a beautiful, unified map of the cosmos. Yet the map was incomplete. As the 20th century progressed, physicists discovered 2 new nuclear forces, the strong and weak forces, which Kaluza and Klein's 5-dimensional framework could not explain. Their elegant universe was too simple to contain the growing complexity of the subatomic world, but the core concept they introduced, the idea of compactified, hidden dimensions, did not fade away. It became the essential seed, waiting for a new and far more complex mathematical language to give it fresh life, a language that would require not 1, but many more dimensions curled up in the fabric of reality itself. The elegant simplicity of Kaluza and Klein's 5-dimensional universe could not hold. Physics had plunged deeper into the quantum realm, discovering a zoo of strange particles and 2 additional fundamental forces that governed the atomic nucleus. The dream of unification, however, did not die. It retreated into the abstract wilderness of mathematics, only to re-emerge decades later in a form far more radical and beautiful. This new framework proposed that the most fundamental ingredients of reality are not tiny dots of matter, but unimaginably small loops of vibrating energy. Think of the strings on a cello. A single string can vibrate at different frequencies, each producing a distinct musical note. Now, imagine if every single particle in the universe, from the humble electron to the lofty photon of light, was not a particle at all, but a different resonant note played on an infinitesimally small vibrating string. An electron is one vibrational pattern, a quark is another. Gravity itself would be the vibration of a closed loop of string. This is the core proposition of superstring theory, a vision where the entire cosmic symphony is composed from these one-dimensional strands of pure energy. For this mathematical symphony to be harmonious, however, it demands a very specific stage. The equations of superstring theory are exquisitely sensitive. When physicists first worked them out, they found the mathematics only produced sensible, consistent predictions if the universe they described had a very particular number of dimensions. Not 4, not 5, the equations flatly refused to balance in any spacetime with fewer than 10 dimensions, 9 dimensions of space and 1 dimension of time. This was not a suggestion or a curious possibility. It was a strict requirement for the theory's internal logical consistency. Without these extra dimensions, the mathematics would produce physical nonsense like probabilities that are less than zero or energies that become infinite. The need for 10 dimensions arises from the delicate dance of quantum mechanics and relativity. To avoid catastrophic anomalies, mathematical inconsistencies that would shatter the theory's predictive power, the strings must vibrate in a spacetime of precisely this dimensionality. So where are these 6 extra spatial dimensions beyond the 3 we move through? Like the curled-up dimension in Kaluza-Klein theory, they are thought to be compactified, curled and twisted upon themselves at the Planck scale, a distance so minuscule that it is a trillion times smaller than an atom. Every single point in our familiar 3-dimensional space may hide an entire 6-dimensional geometric shape, a Calabi-Yau manifold, a landscape of unimaginable complexity folded into a volume so small it is forever beyond our direct perception. We are like ants crawling along the length of a vast, intricate tree root, completely unaware that the root itself is just one filament in a gigantic, hidden tree. The universe, according to this theory, is fundamentally a 10-dimensional entity, and everything we see and feel is merely a 3-dimensional shadow of its true, vibrating nature. The elegance of superstring theory came with a bewildering complication. By the 1990s, physicists realized they were not looking at one single theory of everything but 5. Each version of string theory was mathematically consistent in 10 dimensions, yet they all described different worlds with different rules for how strings could vibrate and interact. It was as if 5 brilliant architects had each designed a perfect blueprint for a cathedral, but no 2 blueprints were for the same building. This was deeply unsettling. If nature is unified, why would its most fundamental description offer 5 separate, competing answers? The impasse seemed absolute until a series of stunning mathematical discoveries revealed a hidden connection. Researchers found that these 5 seemingly distinct theories were not rivals at all. They were different faces of a single, deeper, and more mysterious structure. This unifying framework was named M-theory, where the M stands for mystery, magic, membrane, or matrix, depending on whom you ask. Its most shocking revelation was the need for one more dimension. M-theory does not live in 10 dimensions, it requires 11. This 11th dimension is not like the others. In the 5-string theories, the extra 6 dimensions are curled up into tiny, complex shapes. The 11th dimension proposed by M-theory is different. It can be imagined as a vast new axis of possibility, a direction that allows the 5-string theories to merge into one coherent picture. Think of it this way: you have 5 different maps of the same mountain range. One map shows only the peaks, another shows only the river valleys, a third shows the forest cover. Each seems to depict a completely different landscape, but then you realize these are not maps of different places. They are just different 2-dimensional projections of a single 3-dimensional mountain range. The 11th dimension in M-theory is like that 3rd dimension, providing the height and perspective needed to see how all the flat maps fit together. Within this 11-dimensional spacetime, the fundamental objects are no longer just 1-dimensional strings. M-theory introduces higher-dimensional entities called branes, short for membranes. A 0-dimensional brane is a point, a 1-dimensional brane is a string, a 2-dimensional brane is a sheet or membrane, like a microscopic piece of fabric. These can extend all the way up to 9-dimensional objects. In this richer landscape, our familiar strings can be seen as 1-dimensional slices of these higher-dimensional branes, vibrating in the grand geometry of an 11-dimensional cosmos. The 5 10-dimensional string theories become special cases or different viewpoints of this single 11-dimensional reality, each describing what happens when the 11th dimension is curled up or stretched out in a particular way. With M-theory, the search for hidden dimensions reached a new peak of sophistication. The universe was no longer just a place of tiny, curled-up loops, but a dynamic arena where vast, hidden membranes could exist, and where all possible versions of string theory were unified into one profound and still largely mysterious whole. M-theory's 11-dimensional framework presents a breathtaking possibility, but it leaves a crucial question unanswered. If 6 of these dimensions are curled up into a space smaller than an atom, what exactly do they look like? They are not simply tiny, featureless loops. The mathematics of string theory demands they be folded into shapes of stunning complexity and beauty, geometric forms known as Calabi-Yau manifolds. Picture that garden hose stretching to the horizon once more. From a distance, it appears as a simple line, a 1-dimensional object, but as you approach, you discover its surface is actually a 2-dimensional cylinder, curled into a circle so small you only see it up close. Now amplify that concept into a realm of pure geometry. A Calabi-Yau manifold is the 6-dimensional equivalent of that curled-up surface, but with a richness and intricacy that defies easy visualization. These are not random scrunches of space. They are precise, elegant shapes defined by exquisite mathematical equations, possessing a deep internal symmetry that makes them the only suitable homes for vibrating strings. Think of each point in our familiar 3-dimensional space, every location in your room or in the vast emptiness between stars, not as a mere dot, but as a portal to an entire 6-dimensional universe, a microscopic knot of geometric possibility folded in upon itself. The specific shape of this hidden manifold is not just a curious detail, it is everything. The way a string vibrates is dictated by the geometry of the space it moves through, just as the note played on a guitar string depends on the length and tension of the string itself. In the cosmic symphony, the Calabi-Yau manifold is the instrument. Its exact topology, the number of holes it contains, the twists in its structure, and the patterns of its curvature all determine the resonant frequencies that the strings can adopt. Each distinct vibrational mode corresponds to a different particle with specific properties. One particular pattern of vibration might manifest in our 3-dimensional world as an electron, with its specific mass and negative charge. Another, slightly different resonance could produce a quark or a photon or the mysterious Higgs boson. The physical laws we take for granted, the strengths of the fundamental forces, the existence of 3 families of matter particles, even the value of the cosmological constant that drives the universe's expansion, all of these could be direct consequences of the hidden geometry of a Calabi-Yau shape. This means the entire diversity of our universe, from the stability of atoms to the nuclear reactions powering stars, might be frozen music the eternal echo of strings vibrating in a hidden, six-dimensional landscape we can never directly see. The search for the one true Calabi-Yau manifold that describes our reality is one of the great quests in theoretical physics, because finding it would be like discovering the ultimate musical score for existence itself. Yet the idea of tiny, curled-up dimensions is not the only possibility. There exists a far more dramatic vision, one where the hidden dimensions are not microscopic, but could be astronomically large, even infinite. This is the brane world scenario, and it turns our cosmic self-image completely inside out. In this model, our entire three-dimensional universe with all its galaxies, stars, and planets is not the whole story. It is merely a three-dimensional membrane, a kind of island or sheet, floating within a much larger, higher-dimensional space called the bulk. Think of our universe as a single page from an impossibly large book, drifting in the emptiness of a vast library. We are confined to that page. Every particle of matter, every beam of light, every force except one is stuck to the surface of our brain, unable to escape into the surrounding bulk. This confinement explains why we only perceive three spatial dimensions. We are like ants living on the surface of a leaf, completely unaware of the three-dimensional forest that surrounds it. The one force that is not confined is gravity. In many brane world models, gravity is the sole cosmic traveler, free to leak off our brain and dissipate into the higher dimensional bulk. This single, profound difference could solve one of the oldest puzzles in physics. Why is gravity so unimaginably weak compared to the other fundamental forces? Consider a simple magnet on your refrigerator. That tiny magnet, using the electromagnetic force, can overcome the gravitational pull of the entire planet Earth. Gravity is weaker by a factor of a trillion. In the brane world picture, this weakness is not an intrinsic property of gravity itself, but a consequence of geometry. Most of gravity's influence simply bleeds away into the extra dimensions. What we feel as gravity in our universe is just a tiny remnant, a faint shadow of its full strength, like hearing only a faint echo of a shout because most of the sound has traveled into other rooms. The most famous realization of this idea is the Randall-Sundrum model, proposed by physicists Lisa Randall and Randall-Sundrum. They showed mathematically how a warped or curved extra dimension could naturally trap all standard model particles on our brain, while allowing the graviton, the hypothetical particle that carries the gravitational force, to propagate into the bulk. In their model, the bulk is not a flat, empty space, but is profoundly curved like the space near a massive object but extended into an extra dimension. This curvature creates a kind of gravitational well that pins our brain in place, making it a stable universe. The elegance of this model is breathtaking. It does not require the extra dimensions to be small. They could be infinite in size, yet remain hidden because everything that makes up our reality, except for gravity's gentle whisper, is forever stuck to our three-dimensional slice of existence. We are living on a cosmic membrane, sensing only the vibrations that travel along its surface, while the true depth of reality extends into shadows we can only infer from the puzzling, persistent weakness of a force that holds the very stars together. But if gravity can leak into a higher dimensional bulk, a startling question arises. How large must those hidden dimensions actually be? For decades, the assumption was that any extra spatial dimension had to be inconceivably small, curled up at the Planck scale. Yet a revolutionary idea emerged at the turn of the 21st century, challenging that very foundation. What if some of the extra dimensions are not microscopic, but are almost macroscopic, large enough that we have simply failed to notice them? This is the bold proposition of the Arcani-Hamed, Dimopoulos, and D. Valle model, often called the AD model. They asked a simple, profound question. What if the reason gravity is so weak has nothing to do with its intrinsic strength, but is simply because it spreads out into extra dimensions that are far larger than anyone had dared to consider? In this picture, our universe is a three-dimensional brane, but it floats within a higher dimensional space that has not just one, but several extra dimensions that are relatively large, perhaps as big as a fraction of a millimeter across. To understand the power of this idea, picture a source of light in a dark room. In a three-dimensional room, the light spreads out in all directions, and its intensity diminishes rapidly with distance. Now, imagine that same light source in a space with four large spatial dimensions. The light would spread out into that extra volume as well, diluting its intensity even faster. Gravity in the AD model behaves exactly like that light. It propagates into all the dimensions, including the large extra ones. What we perceive in our three-dimensional brane is just a tiny fraction of gravity's full force, because most of its influence has bled away into the unseen volume next door. This geometric dilution explains its apparent feebleness with elegant simplicity. The most astonishing implication is the proposed size of these dimensions. The AD model suggests they could be as large as 1/10 of a millimeter or even bigger. That may still sound tiny, but in the world of particle physics, it is an astronomical scale. It is a size we could, in principle, probe. If such large extra dimensions exist, they would dramatically alter the behavior of gravity at very short distances. Newton's law of universal gravitation, which says the force weakens with the square of the distance, is a law for a three-dimensional world. In a universe with, say, two large extra dimensions, gravity would weaken with the fourth power of the distance at scales smaller than the size of those dimensions. This means that if you could measure the gravitational pull between two objects separated by a mere fraction of a millimeter, you might witness gravity suddenly becoming stronger than expected as you enter a regime where it is no longer diluted. This has sparked a fascinating frontier of experimental physics. Scientists are now conducting exquisitely sensitive tabletop experiments using tiny, suspended mirrors or oscillating cantilevers to measure gravitational forces at sub-millimeter distances. Simultaneously, the world's most powerful particle colliders, like the Large Hadron Collider, are on the hunt for a different signature. If enough energy is concentrated in a collision, it could theoretically create a particle that carries gravitational force, a graviton, which would then promptly vanish into the large extra dimension, carrying energy and momentum away from our brane. In the detector, this would appear as a mysterious imbalance, a collision where energy seems to simply disappear. The search for these large extra dimensions is a direct empirical test of a once unthinkable idea, probing the possibility that the true architecture of reality extends into realms just beyond our fingertips, hiding in plain sight all along. The search for large extra dimensions opened a thrilling new frontier, but it presented its own profound puzzle. If these dimensions are truly sizable, why does our universe exhibit such an immense gap between the forces that govern the very small and the very large? This is the infamous hierarchy problem. The energy scale where gravity becomes strong, the Planck scale, is a quadrillion times more powerful than the scale of the electroweak force, which dictates particle masses and interactions. In most models, this staggering difference requires an absurdly precise and seemingly random fine-tuning of numbers to 18 decimal places, a coincidence so extreme it feels like a cosmic flaw in our understanding. The Randall-Sundrum model, however, offers a solution of breathtaking elegance, not by adjusting numbers, but by warping the very geometry of a hidden dimension. Imagine our three-dimensional universe as a membrane, but this time picture it floating not in a flat, empty bulk, but within a five-dimensional space that is profoundly curved. This curvature is described by a warped geometry, akin to the surface of a slide that grows exponentially steeper as you move along it. In this model, there are two branes. Our familiar universe, with all its stars and galaxies, resides on one brane called the TV brane. Far across this warped fifth dimension, separated not by vast distance but by steep geometric curvature, lies a second brane, the Planck brane, where gravity is naturally strong. The genius of the model is the warp factor, a mathematical term that exponentially suppresses or dilutes energy scales as you move through the curved dimension. A fundamental mass or energy defined on the distant Planck brane is exponentially reduced by the time its influence reaches our brain. Think of a shout in a vast curved canyon. By the time the sound wave travels across the warped geometry to reach you, it has faded to a whisper. In the Randall-Sundrum universe, the raw, Planck-scale strength of gravity originates on the distant brane, but its force is diluted by an exponential factor of perhaps 60 orders of magnitude as it crosses the warped bulk to reach us. What arrives in our world is the incredibly weak gravity we experience. Conversely, the particles of the standard model are trapped directly on our brain, so their energy scales are not diluted at all. This creates the hierarchy not by chance but by geometry. The immense gap between gravity and the other forces is not a random number plugged into the equations. It is a natural outcome of living on a particular slice of a warped reality. The warping does the fine-tuning for us, using the inherent properties of curved space to generate the vast differences in scale we observe. It is as if the universe solved its most awkward numerical problem, not with a calculator, but with the shape of space itself, hiding the true strength of gravity behind a curtain of geometric distortion in a single, hidden fifth dimension. The warped geometry of brane worlds offers one solution to gravity's weakness, but a far more radical idea suggests the problem lies deeper in our very concept of what a dimension is. This idea emerged not from string theory directly, but from a profound paradox at the edge of a black hole. When an object falls into a black hole, according to classical physics, it is lost forever, its information seemingly erased from the universe. This creates a fundamental conflict with quantum mechanics, which insists that information can never be truly destroyed. In the 1970s, physicist Jacob Bekenstein made a startling proposal. He suggested that the entropy of a black hole, which is a measure of the information it contains, is not proportional to its volume, as one might expect for a three-dimensional object. Instead, it is proportional to the area of its event horizon, the two-dimensional spherical surface that marks its point of no return. This was a bizarre hint that the information content of a three-dimensional region of space might be encoded on its two-dimensional boundary. Decades later, Gerard T. Hooft and Leonard Susskind took this hint and forged it into a revolutionary principle. They proposed that the maximum amount of information you can pack into any region of space is not determined by its volume, but by the area of the surface that encloses it. Think of it like a hologram on your credit card. That shiny, two-dimensional sticker contains all the information needed to project a full, three-dimensional image when light shines on it at the right angle. The holographic principle boldly suggests that our three-dimensional universe might work the same way. All the information that describes everything within a volume of space, every star, every planet, every person, is not actually located within that volume. It is painted pixel by pixel on a distant two-dimensional surface that surrounds it. For a black hole, that surface is its event horizon. For our entire observable universe, it could be the cosmic horizon, the farthest distance from which light has had time to reach us since the Big Bang. This is a staggering inversion of reality. We perceive ourselves living in a three-dimensional world, but according to this principle, we are akin to shadows on a cave wall, or characters in a movie being projected from a cosmic film reel that exists in one less dimension. Our rich, textured experience of depth, distance, and solidity would be an emergent illusion, a magnificent projection from a fundamentally flat reality where the true data of existence is stored. This challenges the most classical notion of all, that dimensions are the fundamental scaffolding of reality. In the holographic view, dimensionality is not primary, it is a consequence. Three dimensions are what emerge when information stored on a two-dimensional surface is processed, much like a three-dimensional video game emerges from the flat, two-dimensional code written by its programmers. The universe, then, might not be built from strings vibrating in hidden dimensions, but from bits of information etched on the ultimate boundary of space itself, rendering our entire cosmic experience a hologram of breathtaking complexity and depth. The holographic principle shatters our classical intuition, suggesting dimensions themselves might be an emergent illusion. But what if the opposite is also true, and the hidden dimensions are not just real, but responsible for generating an almost infinite variety of realities? This brings us to one of the most profound and controversial consequences of string theory, the concept of the landscape. Recall the Calabi-Yau manifolds, those exquisite six-dimensional shapes where strings vibrate. The mathematics does not produce just one perfect shape. It produces a staggering number of them, perhaps 10 to the power of 500 distinct possibilities. That is a 1 followed by 500 zeros, a number so vast it exceeds the count of all the atoms in our observable universe. Each of these shapes represents a different way for the extra dimensions to be compactified, and each configuration yields a different set of resonant frequencies for the strings. In our universe, that resonance dictates the laws of physics as we know them, the mass of the electron, the strength of gravity, the existence of three dimensions of space. But on a different Calabi-Yau manifold with a different topology, the strings would vibrate to an entirely different tune. The constants of nature would have different values. The fundamental forces might be stronger, weaker, or not exist at all in the forms we recognize. Some configurations might allow for stable atoms and complex chemistry, leading to stars and planets and life. Others might be barren, empty, or unstable, collapsing instantly into nothingness. This colossal collection of every possible vacuum state, every possible set of physical laws that string theory allows, is what physicists call the landscape. It is not a physical place you could travel to, but a mathematical map of all conceivable universes permitted by the theory's equations. If our universe is described by just one point on this map, one specific Calabi-Yau shape, a monumental question arises. Why this one? Why do we inhabit a universe with exactly these laws, these constants that allow for our existence? One compelling answer emerges from the landscape itself, an answer that requires us to think on a truly cosmic scale. In the context of eternal inflation, the theory that our Big Bang was just one bubble in a forever expanding cosmic foam, each of these vacuum states in the landscape can be realized as a separate, expanding bubble universe. Imagine a pot of water beginning to boil. Bubbles of steam form, expand, and rise to the surface. Each bubble has its own internal environment. In the cosmic analogy, each bubble is a separate pocket universe, born from the fluctuating energy of a quantum vacuum, and each one crystallizes with a random Calabi-Yau compactification as it forms. The geometry of its hidden 6 dimensions is frozen in at birth, locking in its unique set of physical laws. Our entire observable cosmos would then be just one bubble among an infinite froth of others, each with its own dimensional architecture and its own version of reality. In some, gravity might be so strong that stars form and burn out in an instant. In others, the nuclear forces might be too weak to bind protons and neutrons, leaving only a sea of hydrogen. We find ourselves in a bubble where the numbers are just right for complexity to arise, not because of design, but simply because in a multiverse of infinite variety, every possible combination must exist somewhere. The hidden dimensions, therefore, become the ultimate architects of diversity. Their specific, curled-up geometry in each bubble dictates what kind of universe unfolds within it. What we perceive as the fundamental, unchanging laws of nature may be nothing more than local bylaws, the unique product of a dimensional twist that happened in our corner of a reality so vast and varied it defies human comprehension. Yet the landscape of infinite possibilities raises a profound question about our own cosmic origin. What if the Big Bang was not a singular, explosive beginning from nothing, but merely the latest chapter in an endless cosmic cycle? This is the vision of cyclic cosmology, a theory where hidden dimensions are not passive backdrops, but the dynamic stage for the universe's most violent and creative act. The story begins with two parallel worlds, each a three-dimensional brane like our own, floating in a higher dimensional bulk. They are separated by a tiny gap along a hidden fourth spatial dimension, drifting silently through the emptiness. Over eons, these two branes are drawn together by a gentle force, perhaps a spring-like tension in the bulk itself. They move closer and closer until finally they collide. The impact is not a destructive crash of solid objects, but a transfer of immense kinetic energy into the fabric of the branes themselves. This collision, this meeting of two three-dimensional worlds along a hidden fourth dimension, is what we call the Big Bang. In that cataclysmic moment, the branes rebound, flooded with an intense heat and density that seeds the matter and radiation of a new cosmos. This model, known as the ekpyrotic universe from the Greek word for conflagration, reimagines our beginning not as a singularity but as a brane collision. The beauty of this idea lies in its cyclical nature. After the collision, the branes bounce apart and the new universe begins its long expansion, just as ours has for 13.8 billion years. Galaxies form, stars burn, and eventually, over trillions of years, the universe cools and grows dark, its energy diluted by endless expansion. But the story does not end in eternal cold and silence. The same gentle force that drew the branes together once before begins to act again. Across the vast gulf of the bulk, the two branes are pulled slowly back toward each other. The universe contracts not by galaxies rushing together, but by the very space of our brane being drawn taut as it approaches its parallel neighbor. Finally, they collide once more, igniting a new Big Bang and birthing a fresh universe from the ashes of the old. This cycle of expansion, cooling, contraction, and collision could repeat forever, an eternal cosmic heartbeat with no true beginning and no end. In this view, hidden dimensions are the essential mechanism of rebirth. The higher dimensional bulk is the theater, and the moving branes are the actors in a drama that resets the cosmos. Each cycle need not be an exact copy of the last. The collision might impart slightly different energies, leading to variations in the physical constants or the arrangement of matter in the new universe. Our existence, with its specific laws and conditions, could be the product of one particular bounce in an endless sequence. This model offers a compelling alternative to a single, finite beginning, suggesting our universe is part of an older, grander process where dimensions themselves are the agents of cosmic renewal, forever weaving and reweaving the fabric of reality in an infinite dynamic loop. Our cosmic journey has explored dimensions curled into knots and stretched across warped geometries, but perhaps the most unsettling possibility is that the stage itself is not physical at all. What if the three spatial dimensions and one time dimension we navigate are not fundamental features of reality, but merely the user interface of a vast simulation? This is the simulation hypothesis, a modern philosophical idea that reframes the quest for hidden dimensions in a startlingly digital light. Proponents like philosopher Nick Bostrom present a sobering statistical argument. If a civilization ever reaches a technological level capable of creating detailed, conscious simulations of its own history, and if such civilizations have any interest in running such simulations, then the number of simulated minds would vastly outnumber the biological ones. Statistically, we are far more likely to be among the simulated beings than the original creators. In this view, our universe is not built from strings or branes, but from bits. The apparent smoothness of space and the flow of time are not primary realities, but emergent properties of a cosmic computation running on some unfathomable substrate. The laws of physics are not discovered, they are programmed, the consistent rules of the simulation's engine. This perspective forces us to reconsider what a hidden dimension might actually be. If our reality is a simulation, then the true hidden dimensions are not curled up spatial directions, but the foundational parameters of the hardware running the code. The simulator's reality might operate with a completely different number of spatial dimensions, perhaps far more, or perhaps even fewer. Our rich, three-dimensional experience could be a high-resolution projection from a system that exists in a realm of pure information, where concepts like distance and volume are just convenient abstractions for organizing data. Imagine a modern video game. The world you explore appears to have depth, mountains, and valleys, a full three-dimensional landscape. Yet the foundational reality of that game is the two-dimensional architecture of its computer code and the silicon circuits of the processor. The game world has its own consistent physics like gravity and momentum, but those are just algorithms, not fundamental forces. From the perspective of a character inside the game, the computer's motherboard and its electrical pathways are the hidden dimensions, utterly inaccessible yet absolutely essential for its existence. The simulation hypothesis takes this analogy to its ultimate conclusion. It suggests that the quest to understand the hidden dimensions of our universe might be akin to that video game character trying to deduce the properties of the computer chip by carefully measuring the falling speed of virtual apples. We are probing the shadows on the cave wall, trying to infer the nature of the fire and the puppeteers. This idea transforms the mystery of our existence into a computational puzzle. The puzzling discreteness of quantum mechanics, where energy comes in tiny packets, could be seen as evidence of a finite resolution like the pixels on a screen. The speed of light, an absolute cosmic speed limit, might be the processor clock rate, the maximum speed at which information can be updated across the simulation. Even the bizarre findings of quantum entanglement, where particles instantaneously influence each other across vast distances, could be explained by the system accessing a shared variable in its base code, a shortcut that bypasses the rendered three-dimensional space entirely. While this remains a deeply speculative philosophy rather than a testable physical theory, it challenges our most basic assumptions. If true, the ultimate hidden dimensions are not out there in space, but in the logical framework of a reality we can never directly access, a reminder that the nature of existence itself might be far stranger than any geometry we can conceive. The simulation hypothesis pushes our conception of reality to a digital extreme. But what if the dimensions of space and time are not programmed, but stitched together from something even more basic? This is the promise of a radically different approach called causal dynamical triangulations. While string theory and brane worlds begin by assuming a fixed number of dimensions as a starting stage, this framework asks a more fundamental question. What if dimensionality is not an assumption at all, but an end result, something that emerges from the chaotic quantum dance of spacetime itself? To find out, physicists using this method start with almost nothing. They model the fabric of reality not as a smooth continuum, but as a vast, shifting network of the simplest geometric shapes imaginable, tiny triangular blocks called simplices. Think of it as building the universe from a cosmic bucket of Lego, but where every piece is a microscopic triangular tile of spacetime. The rules are simple but profound. These tiles can only connect to one another in specific ways that preserve causality, the unbreakable law that cause must always precede effect. This ensures that the network always has an inbuilt direction of time, a consistent flow from past to future woven into its very connections. Then, using the powerful tools of quantum mechanics, the model allows this network to fluctuate. Trillions upon trillions of possible configurations, different ways the triangles can snap together, are summed over in a grand quantum calculation. The outcome is breathtaking. When you zoom out and look at the average properties of this roiling quantum foam on the large scales we experience, something remarkable happens. The chaotic network spontaneously crystallizes into a smooth, classical geometry that behaves exactly like our familiar four-dimensional spacetime, with 3 dimensions of space and 1 of time. The dimensionality we take for granted is not put in by hand. It emerges from the collective behavior of the network, much like the smooth, continuous surface of a pond emerges from the chaotic motion of countless water molecules. But the real surprise lies at the very smallest scales, at the Planck length. When the model examines the effective dimensionality of spacetime in this ultra-microscopic regime, it does not find 4 dimensions. The calculations suggest it shrinks, appearing to approach a value of just 2. This is a staggering result. It implies that at the most fundamental level, the fabric of reality might be effectively 2-dimensional. The rich 3-dimensional space we move through could be a kind of illusion that only solidifies as you zoom out, like a pointillist painting that resolves into a detailed image only when viewed from a distance. In this view, dimensionality is not a fixed, eternal setting of the cosmos. It is a dynamic, fluctuating property, a temperature reading of spacetime's quantum frenzy. At high energies and tiny scales, the universe might shed dimensions, becoming simpler and more primitive. As things cool and expand, those dimensions freeze into place, giving us the stable, 4-dimensional stage upon which the cosmic drama unfolds. This paints a picture where the hidden dimensions are not curled up in space, but hidden in scale, revealing that the very concept of dimension is far more fluid and mysterious than we ever imagined. While causal dynamical triangulations suggests dimensionality emerges from chaos, another profound idea seeks to bring order to the very heart of the problem. For decades, the quest to merge gravity with quantum mechanics has been dominated by string theory and its extra dimensions, but there exists a compelling alternative that asks a radically different question. What if Einstein's theory of general relativity is already complete? And the problem is not that it breaks down at the quantum scale, but that we have not yet understood how to properly extend its mathematics into that wild domain. This is the ambitious goal of a framework known as asymptotic safety in quantum gravity. The central challenge in quantizing gravity is a phenomenon called non-renormalizability. In simpler terms, when you try to apply the standard quantum rulebook to Einstein's equations, you get infinities that cannot be sensibly removed. It is like trying to calculate the exact cost of a project, but every time you account for a new detail, the price tag jumps to an infinite number. String theory solves this by replacing point particles with extended strings and adding extra dimensions. Asymptotic safety proposes a different solution entirely. It suggests that gravity's strength, its so-called coupling constant, does not run wild into infinity as you probe higher energies. Instead, it flows toward a special, self-regulating value called a fixed point. Imagine a river rushing toward a waterfall, representing the plunge into the quantum realm where our theories break down. Asymptotic safety proposes that before the river goes over the edge, it is guided into a stable, swirling whirlpool, a fixed point. Within this whirlpool, the turbulent waters become predictable and finite. The theory becomes well-behaved at all energy scales, from the everyday to the Planck scale, without the need for any new particles or hidden dimensions. The mathematics of this is governed by the renormalization group flow, which is essentially a map of how a theory's parameters change as you zoom in or out, much like how the rules of a game might change if you are playing on a continent versus in a single city. For gravity to be asymptotically safe, its flow must be drawn toward this special fixed point at high energies, taming the infinities and allowing calculations to make sense. Within some versions of this framework, a fascinating side effect emerges. As you follow this flow from low energy to high energy, the effective dimension of spacetime itself might not stay fixed at 4. Research suggests that the number of dimensions could become a scale-dependent property. At the energies and distances we experience, spacetime appears firmly 4-dimensional. But if you could theoretically probe the universe at much higher energies, closer to the Planck scale, the fabric of reality might appear to have a lower effective dimension, perhaps even shrinking toward 2 dimensions. This is not because extra dimensions are curled up, but because the very nature of the gravitational interaction changes how we perceive the geometry. Think of it like observing a ball of steel wool. From a distance, it looks like a solid 3-dimensional sphere, but as you move closer, you see it is mostly empty space, a tangled mesh of 1-dimensional fibers. Its effective dimension, in terms of how things move through it or interact with it, changes with your scale of observation. Asymptotic safety paints a picture where the stage of reality is not static but fluid. The dimensions we count are not an absolute feature of the universe, but a perspective that shifts with the energy of our inquiry, revealing a cosmos whose fundamental architecture is both resilient and wonderfully adaptable. The smooth, continuous stage of spacetime is a comforting illusion. In our daily lives, we navigate dimensions as if they were simple, classical coordinates, like the grid lines on a map. Yet just as quantum mechanics revealed that particles are not tiny billiard balls but probabilistic waves, some physicists suspect that spacetime itself may have a quantum identity. This leads us to a fascinating and abstract frontier, where the very coordinates of reality stop obeying our familiar rules of arithmetic. In the mathematics we all learned, multiplication is commutative. 3 times 4 equals 4 times 3. The order does not matter, but in the quantum world, this simple rule breaks down. The most famous example is the Heisenberg uncertainty principle, which states that you cannot simultaneously know both the exact position and the exact momentum of a particle. This is not a technological limitation, it is woven into the fabric of reality. Mathematically, it arises because the operators representing position and momentum do not commute. Their product depends on the order you apply them. Position times momentum does not equal momentum times position. This non-commutative property is the algebraic heartbeat of quantum weirdness. Now, a profound idea extends this principle to the stage itself. What if the coordinates of spacetime, the very labels for here and there, now and then, also fail to commute at the tiniest possible scales? This is the core of non-commutative geometry, a framework developed by mathematician Elaine Connes. In this view, as you approach the Planck scale, the fabric of reality ceases to be a smooth, continuous manifold. Instead, spacetime becomes granular or foamy. The concept of measuring a precise location in a smooth, infinite continuum loses its meaning. In this regime, the coordinates x and y, which label points in space, may no longer commute. X times y would not equal y times x. This is a staggering notion. It implies that at the fundamental level, there is a built-in fuzziness to geometry itself. You cannot pin down a point with infinite precision because the very act of measurement disturbs the spacetime coordinate you are trying to measure. Much like trying to measure the position of an electron changes its momentum. This granularity suggests that the smooth, continuous dimensions of Einstein's relativity are not fundamental. They are an emergent, large-scale approximation, like the smooth appearance of a photograph that is actually made of discrete pixels when you zoom in. The true, hidden structure of reality, according to this theory, is not geometric in the classical sense. It is algebraic. Dimensions do not exist first as a backdrop. Instead, they emerge from the spectral properties of abstract mathematical operators. Think of it like listening to a symphony. You do not hear the individual air molecules. You perceive emergent properties like pitch, melody, and harmony. In non-commutative geometry, the smooth experience of 3-dimensional space and flowing time is the melody that emerges from the chaotic, non-commutative quantum notes playing at the Planck scale. The algebra is the fundamental score, and the geometry we perceive is the beautiful, coherent sound that arises from it. This transforms our search for hidden dimensions from a hunt for curled-up spatial directions into a deciphering of a deeper, more cryptic code, a mathematical structure where the very concepts of here and there are born from relationships that defy our classical intuition. The granular, non-commutative nature of reality suggests the stage itself is a quantum construction. This leads to a profound shift in perspective, one that turns our cosmic story inside out. Perhaps spacetime and its dimensions are not the foundation of the universe at all. What if they are emergent phenomena, collective illusions that arise from something far more basic, like the way the warmth and pressure of a gas emerge from the chaotic dance of countless invisible molecules? This is the emergent spacetime paradigm, a revolutionary idea that asks us to forget the stage and look instead at the actors. For centuries, physics treated space and time as the absolute backdrop against which the drama of particles and forces played out. Einstein wove them together into a dynamic fabric, but it was still the foundational fabric. The emergent paradigm challenges this hierarchy. It proposes that spacetime is not fundamental. It is a secondary, large-scale effect that condenses out of a more primitive quantum reality, much like liquid water emerges from a network of H2O molecules, or temperature emerges from the average kinetic energy of atoms. In this view, the smooth continuity of three dimensions and the steady flow of time are not givens. They are approximations that work beautifully at our human scale, but dissolve into something else entirely at the quantum level. One of the most compelling pathways to emergent spacetime comes from a seemingly unrelated quantum phenomenon, entanglement. This is the spooky connection where two particles become linked so that measuring the state of one instantly determines the state of the other, regardless of the distance between them. For decades, entanglement was seen as a bizarre but isolated feature of the quantum world. Now, researchers like Mark van Romsdonk have proposed it might be the very glue that stitches spacetime together. The mathematics suggests a stunning possibility that the geometric connection between 2 points in space, the very distance between them, is directly related to how entangled the quantum fields are at those locations. More entanglement between regions translates to a shorter, tighter geometric connection. Less entanglement means the space is effectively farther apart. In an extreme thought experiment, if you could somehow sever all the quantum entanglement between two regions, the space between them would not just expand, it would tear apart entirely, like a piece of fabric unraveling when its threads are cut. From this vantage point, the three-dimensional geometry we navigate is not primary. It is a map of the entanglement relationships between the underlying quantum information. The dimension of depth itself could be a manifestation of how deeply and complexly the quantum data is woven together. This transforms our understanding of what a dimension truly is. In the emergent view, dimensions are not independent directions pre-existing for things to move through. They are consequences. They are the organized patterns that arise when a vast number of quantum bits or qubits become entangled in specific, stable networks. Think of a bustling city seen from a high altitude. You see streets, neighborhoods, and parks, a clear two-dimensional layout, but that layout did not come first. It emerged from millions of individual decisions, relationships, and pathways taken by the people living there. The map is a consequence of their interactions. In the same way, our three-dimensional spatial map could be a consequence of the interactions, the entanglement between countless fundamental quantum entities. The dimension of time may emerge from the way this network of correlations evolves and updates, creating a consistent sequence of cause and effect that we perceive as a flowing present. This paradigm offers a radical resolution to the conflict between quantum mechanics and gravity. Gravity, in Einstein's theory, is the curvature of spacetime. If spacetime itself is not fundamental but emerges from quantum entanglement, then gravity must also be an emergent force. It would not be a fundamental interaction like electromagnetism, but a collective thermodynamic effect, akin to the way elasticity emerges in a solid from the electromagnetic forces between atoms. This perspective is being actively explored through tools like the ADS-CFT correspondence, a mathematical duality that shows how a theory of gravity in a certain curved spacetime can be perfectly equivalent to a quantum field theory without gravity living on its lower dimensional boundary. It is a concrete example of a higher dimensional geometric world, complete with gravity, emerging from the interactions of quantum particles in a world with fewer dimensions. The very fabric of space and its dimensions are being woven, thread by thread, from the quantum connections we once thought played out upon it. We are left with a universe where the stage is built by the play, a cosmic dance where the dancers create the floor beneath their feet with every entangled step they take. The emergence of spacetime from quantum entanglement reveals a cosmos built from connection. But what if the connections themselves point to a deeper, more symmetrical foundation? Our exploration of hidden dimensions has so far dealt entirely with spatial extensions, new directions we could theoretically move through if we were small enough or had the right tools. Yet the mathematics of unification hints at a far stranger possibility, that dimensions are not solely spatial at all. There exists another category entirely, dimensions of a qualitatively different kind that are woven into the very nature of particles themselves. To understand this, we must meet the two fundamental families that make up our universe. On one side are the fermions, the particles of matter. Electrons, quarks, and neutrinos are all fermions. They are the solid stuff of reality, the building blocks of atoms, planets, and people. They are inherently solitary, obeying the Pauli exclusion principle, which prevents two identical fermions from occupying the same quantum state, the reason why matter has structure and volume. On the other side are the bosons, the particles that carry forces. Photons carry electromagnetism, gluons carry the strong nuclear force, the hypothetical graviton would carry gravity. Bosons are the social butterflies of the particle world, able to pile on top of each other without limit, enabling the transmission of energy and force across the void. In our standard model, these two families are utterly distinct, speaking different quantum languages and following different rules. This separation is elegant, but many physicists suspect it is not the final word. They propose a grand, underlying symmetry that would unite these two worlds into one, a principle called supersymmetry. Supersymmetry is a profound mathematical hypothesis that posits a deep, hidden relationship between fermions and bosons. For every known fermion, there should exist a supersymmetric bosonic partner. For every known boson, there should exist a supersymmetric fermionic partner. An electron, a fermion, would have a bosonic partner called a selectron. A photon, a boson, would have a fermionic partner called a photino. This symmetry is so powerful and restrictive that it solves several major theoretical problems at once, from stabilizing the mass of the Higgs boson to providing a natural candidate for the mysterious dark matter that holds galaxies together. To make this symmetry mathematically consistent, however, requires us to expand our concept of spacetime in a radical new way. The equations of supersymmetry demand that we add new dimensions to the fabric of reality, but these are not extra spatial dimensions like the curled-up Calabi-Yau manifolds. They are called supersymmetric dimensions or fermionic dimensions. Unlike our familiar spatial dimensions where coordinates commute, meaning the order of measurement does not matter, these new dimensions are anti-commuting. This is a subtle but profound mathematical distinction. In an anti-commuting dimension, moving a little bit along it and then a little bit along a regular spatial dimension is not the same as doing those steps in reverse order. It produces a minus sign, a fundamental difference that encodes the quantum statistical properties separating fermions from bosons. You cannot visualize these dimensions as tiny curled-up circles or vast, warped bulks. They are not dimensions you could ever walk along. Instead, think of them as hidden degrees of freedom attached to every point in space, new directions in an abstract realm of quantum possibility. If a regular spatial dimension answers the question where, a fermionic dimension answers a question more like what kind. It is a dimension that tracks the difference between matter and force. When a particle moves through this fermionic dimension, it does not change its location in space. It transforms its very identity, flipping from a fermion to its bosonic superpartner or vice versa. In this breathtakingly symmetric universe, the distinction between a particle of matter and a particle of force becomes a matter of perspective, a rotation in a higher dimensional space that includes these strange, anti-commuting directions. The superpartners predicted by this theory are not merely extra particles, they are shadows of our known particles cast along these hidden fermionic axes. While experiments at the Large Hadron Collider have yet to find direct evidence for these superpartners, the mathematical elegance of supersymmetry and its required fermionic dimensions remains a compelling guidepost on the path to a fully unified theory, suggesting that the ultimate architecture of reality may be built from symmetries so deep they require us to reinvent what a dimension means. Supersymmetry's hidden fermionic dimensions propose a profound unity, but they are not the only path toward a single, all-encompassing framework. From the fringes of theoretical physics comes a vision of unification so audacious and visually stunning that it challenges the very complexity of mainstream string theory. This is physicist and surfer Garrett Lissie's An Exceptionally Simple Theory of Everything, a proposal that attempts to weave all known particles and forces into the geometry of a single, breathtaking mathematical object, the E8 Lie group. To understand the ambition here, we must first grasp what a Lie group represents. In mathematics, a Lie group is a type of symmetry group, a set of transformations you can perform on an object that leave it looking the same. Think of a perfect sphere. You can rotate it any amount around any axis through its center, and it remains a sphere. The set of all possible rotations forms a rotation group, a kind of symmetry. Now, imagine a symmetry so rich and multifaceted that it cannot be visualized in our three-dimensional space. The E8 group is one of the most complex and beautiful of these exceptional symmetry structures. It exists in 248 dimensions. This is not a space with 248 spatial directions in the conventional sense, but an abstract mathematical space where each dimension represents a different possible symmetry transformation or a distinct quantum state. Lissie's radical proposal is that every single elementary particle and force carrier in our universe, from the electron to the Higgs boson, from the photon to the gluon, corresponds to a specific point or a particular symmetry within this colossal E8 structure. In this model, our familiar four-dimensional spacetime and all the quantum fields that fill it are not the foundation. They are a kind of shadow, a four-dimensional subset or a particular projection of this vastly larger, 248-dimensional symmetrical reality. Imagine a magnificent, intricate chandelier with 248 perfectly arranged crystals, each catching the light from a single source. Our physical universe, with its handful of particles and forces, is like the pattern of light and shadow that this chandelier casts on a simple, four-dimensional wall. The chandelier itself, the full E8 geometry, is the true, unified object. The theory's power lies in its potential to derive the seemingly random quantum numbers of the standard model particles, like their electric charge and spin, purely from their positions and relationships within this geometric shape. Each particle finds its place as a vertex on the E8 polytope, a multi-dimensional shape whose symmetries dictate how particles can interact and transform into one another. Gravity and the other forces emerge naturally from the curvature and connections within this framework, suggesting that force itself is a geometric phenomenon, much like in Einstein's relativity, but operating in this abstract high-dimensional realm. While Lissie's theory remains highly controversial, criticized for lacking a complete dynamic mechanism and for not yet making unique testable predictions that differ from the standard model, its aesthetic and conceptual appeal is undeniable. It presents a universe where the baffling complexity of particle physics is not a messy accident, but the elegant consequence of a single, sublime mathematical truth. It argues that the hidden dimensions of existence may not be curled up in space or encoded in fermionic directions, but are the very symmetries that define what a particle is, a cosmic code written in geometry so pure that our reality is just one stanza of its infinite poem. The elegant symmetries of E8 propose a universe of pure geometry, but what if the cycles of creation and dissolution are not driven by brane collisions, but by a gentle, geometric reset that erases the scale of the cosmos itself? This is the heart of Roger Penrose's conformal cyclic cosmology, a model where the universe experiences not a single explosive birth, but an infinite series of eons, each one a complete universe from its own Big Bang to its ultimate fade into darkness. Penrose's vision hinges on a subtle but profound property of geometry known as conformal symmetry. Imagine taking a detailed map of a continent and shrinking it down to the size of a postage stamp. All the distances are drastically reduced and all the landmarks are brought incredibly close together, but the angles between every coastline, every mountain range, and every river remain exactly the same. This preservation of angles, regardless of scale, is the essence of conformal geometry. It allows you to rescale a structure to any size without distorting its shape. Penrose applies this principle to the entire cosmos. In the far, far future of our universe, trillions upon trillions of years from now, all matter will have decayed or been swallowed by black holes, which themselves will slowly evaporate via Hawking radiation. The universe will be an ever-expanding, nearly empty sea of extremely low-energy photons and gravitons, a state of maximum entropy and perfect uniformity. In this cold, dark, and vastly stretched-out end, something remarkable happens from a geometric perspective, because there are no massive particles left to define a fixed scale of length or time. The universe becomes effectively scale invariant. The immense distances between the last remaining particles become meaningless. In this conformally symmetric state, the infinite future of our eon becomes geometrically identical to the high-energy, ultra-dense singularity of a Big Bang, if you simply rescale all distances appropriately. Think of a balloon deflated to a single, wrinkled point. That point contains all the information of the balloon's previous surface, but at a completely different scale. Penrose proposes that the conformally invariant end of one eon can be seamlessly attached or conformally matched to the beginning of the next. The infinite future of the old universe is geometrically identified with the Big Bang singularity of the new. This is not a violent collision or a bounce, but a smooth, mathematical continuation where the very concept of scale is rebooted. In this transition, information and structure from the previous eon are not annihilated. They may traverse the boundary in an encoded form. The most striking evidence Penrose and his colleagues have searched for is in the cosmic microwave background, the afterglow of our own Big Bang. They suggest that concentric circular patterns of slightly different temperature in this background radiation could be the gravitational wave imprints of supermassive black hole collisions from the eon that preceded ours. These titanic events, rescaled through the conformal bridge, would leave faint, ghostly circles on the first light of our own cosmos, a message from a previous universe written in the geometry of the sky. This model suggests a hidden dimensional bridge between cosmic epochs that is not a spatial dimension, but a transformational one. The bridge is the conformal scaling itself, a process that allows the entire informational content of a dead universe to be compressed into a seed for a new one, all while preserving the essential relationships that define its structure. Our universe's vast history of stars, galaxies, and life may be one chapter in an infinite book, where the turning of the page is not an explosion, but a quiet geometric transformation, a cosmic sigh between eons. The smooth transition from one cosmic eon to another rests on a deep geometric principle, yet it leaves a more intimate mystery untouched. Why does our own daily reality feel so solid and definite when its quantum foundations are famously fuzzy and probabilistic? This is the infamous measurement problem, the unresolved heart of quantum mechanics. At the subatomic level, particles exist in a superposition of many possible states at once, like a spinning coin that is both heads and tails. Only when observed or measured does this wave function collapse into a single, definite outcome. But what constitutes a measurement, and who or what gets to be the observer? This quandary suggests that objective reality, the shared classical world we all agree upon, might itself be an emergent phenomenon. A compelling answer is emerging from the study of quantum information, a framework called quantum Darwinism. It proposes that the classical world solidifies not through a mysterious collapse, but through a process of natural selection for information. When a quantum system interacts with its environment, which is a vast collection of particles like photons, air molecules, or the cosmic microwave background, information about the system gets copied over and over again into countless fragments of that environment. Think of a stone dropped into a pond. The splash is the quantum event, but the reality of that splash is defined by the countless ripples that spread outward, each one carrying a copy of the information about the stone's impact. In quantum Darwinism, a quantum property becomes objective, becomes real in the classical sense, not when a conscious observer looks at it, but when information about that property is redundantly imprinted onto the environment. These multiple, robust copies are then available for many different observers to independently access and agree upon. You see a tree in the park not because your glance collapses its wave function, but because sunlight has scattered off that tree for hours, imprinting its shape, color, and location onto trillions of photons that have traveled in all directions. Your eyes simply intercept a tiny sample of those countless environmental records. The tree is objective because its information has been widely disseminated and copied. This framework transforms the measurement problem from a philosophical paradox into a dynamic process of information propagation. Now, extend this powerful idea to the very structure of spacetime. Our universe began in a hot, dense quantum state where all possibilities, including every possible configuration of dimensions and physical laws, existed in a vast superposition. This was the ultimate quantum soup. According to quantum Darwinism, not all quantum states are equally fit to produce redundant copies of themselves in the evolving environmental landscape of the early cosmos. Some geometric configurations, some ways of knitting together dimensions, would be more stable, more prone to creating multiple copies of their defining information as the universe cooled and expanded. Our particular configuration, with its 3 stable spatial dimensions and 1 flowing dimension of time, may have been the one that was most successfully replicated. It was the genetic code that proved most robust, outcompeting other dimensional possibilities in the environmental marketplace of the infant universe. The other potential realities, the universes with 4 large spatial dimensions or 2 dimensions of time, simply failed to make enough copies of themselves. They were hidden not by being curled up or existing in another bubble, but by being informationally unfit, unable to redundantly imprint their structure onto the cosmic environment in a way that could be observed and agreed upon. In this view, the classical 4-dimensional stage we take for granted is the grand prize winner in a cosmic competition. It is the reality that was most effective at making itself known, at broadcasting its dimensional signature so widely and redundantly that it became the only objective truth for any potential observer within it. The hidden dimensions are not elsewhere, they are the losers in a Darwinian struggle for informational existence, fading from view not by force, but by a lack of persistence in the quantum memory of the cosmos. Quantum Darwinism suggests our reality won a battle for persistence, but the victor may be built from a fabric riddled with secret passageways. the most intense conflict over the nature of that fabric erupted from a seemingly simple question. What happens to the information that describes an object when it falls into a black hole? This ignited the black hole information paradox, a puzzle so deep it threatened to unravel the foundations of physics. On one hand, quantum mechanics decrees that information is sacred, never destroyed. On the other, general relativity suggests that when something passes a black hole's event horizon, it is lost forever to the outside universe, its information ultimately erased when the black hole evaporates via Hawking radiation. To resolve this, some physicists proposed a radical and violent solution, the firewall paradox. They argued that to preserve information, the event horizon could not be the smooth, uneventful gateway predicted by Einstein. Instead, it must be a searing wall of high-energy particles, a literal firewall that would incinerate anything attempting to cross. This was a deeply unsatisfying idea, pitting one law of physics against another in a cosmic dead zone. From this conflict, a breathtakingly elegant possibility emerged, known as the ER equals EPR conjecture. This deceptively simple equation proposes a profound union between two of the most iconic ideas in physics. EPR, named for Einstein, Podolsky, and Rosen, represents quantum entanglement, that spooky connection where particles remain linked across vast distances. ER for Einstein and Rosen represents the wormhole, a bridge through spacetime connecting two distant points, also known as an Einstein-Rosen bridge. The conjecture boldly states that these are not two different phenomena. They are the same thing described in two different languages. A pair of entangled particles, like two electrons with perfectly correlated spins, are not communicating faster than light through empty space. They are connected by an unimaginably tiny wormhole, a Planck-scale bridge in the fabric of reality. This wormhole is not a tunnel you could travel through. It is a geometric manifestation of the quantum link itself. Think of it this way: you have two separate sheets of paper, each representing a location in our three-dimensional space. They lie flat on a table far apart. Now picture a tiny, straw-like structure in a higher dimensional space that connects a point on one sheet to a point on the other. From the perspective of someone living on the two-dimensional surface of either sheet, the connection is invisible. They only see two separate points that mysteriously influence each other instantly. But from the higher dimensional view, the connection is geometric, a shortcut through the bulk. ER equals EPR suggests our universe operates on this principle. The entanglement that stitches together the quantum vacuum and gives rise to emergent spacetime might do so by weaving a dense network of these microscopic wormholes. Every quantum connection is a thread, and each thread is a hidden dimensional bridge. This transforms our understanding of what a dimension can be. It suggests that the hidden architecture of reality is not just made of curled-up circles or warped bulks, but of an ever-changing web of connections. The dimension of distance between two entangled particles is, in a fundamental sense, an illusion. They are adjacent via a shortcut in a higher dimensional geometry we do not perceive. In this view, the universe is less like a static stage and more like a dynamic neural network, where the strength of a connection, the weight of a synapse, is equivalent to the geometry of a hidden bridge. The paradox of the black hole firewall may then be resolved not by destruction but by connection. The information of what falls in is not burned away, but is preserved through a complex tangle of wormholes linking the interior of the black hole to the Hawking radiation it emits outside. The horizon might be a turbulent place, but not necessarily a lethal one, as information travels through these hidden geometric pathways. This conjecture offers a stunning synthesis, where the weirdest feature of the small-scale quantum world and the most dramatic prediction of large-scale relativity are revealed as two faces of a single, deeper truth, a reality where correlation is literally a dimension in disguise. The seamless web of wormholes connecting entangled particles hints at a reality where all dimensions are interwoven, yet one dimension stands apart in our daily experience. Time flows with an undeniable urgency, an arrow pointing from past to future that seems as fundamental as the three dimensions of space. But what if this flow is the grandest illusion of all, a shadow cast by a timeless foundation? At the deepest level, where quantum mechanics and gravity must finally meet, the equations begin to erase time itself. The Wheeler-DeWitt equation, a landmark attempt to quantize general relativity, presents a universe frozen in an eternal now. In this profound formulation, time does not appear as a variable. The equation describes the quantum state of the entire cosmos, but it is static, like a single, unchanging frame from a film. There is no tick of a clock, no before or after. This timelessness is known as the problem of time in quantum gravity, and it suggests that our relentless experience of temporal flow is not a feature of the fundamental architecture. It is something that emerges, condensing out of the quantum fog when we zoom out to the world we inhabit. So how does time arise from a timeless base? One compelling answer lies in the concept of correlations. Imagine a timeless block of marble. Within it, a sculptor sees the potential for a statue. By carving relationships between different points on the marble, creating contours and depths, the illusion of a figure in motion is born. In a similar way, our experience of time may emerge from the changing relationships, the quantum correlations between different parts of the universe. As these correlations evolve, one configuration acts as a clock for another. The position of a pendulum, the decay of an atom, the expansion of space, these are not happening within time, they are what define time. Each process provides a reference against which others are measured, weaving the tapestry of sequence and duration we perceive. Another powerful perspective comes from thermodynamics, the science of heat and disorder. The second law states that entropy, or disorder, always increases in an isolated system, giving time its irreversible arrow. We remember the past, not the future, because the past was a state of lower entropy. This thermodynamic gradient, from order to disorder, may be the very engine that generates the feeling of temporal passage. In a universe that began in an exceptionally smooth, low-entropy state, the subsequent drive toward higher entropy creates all the processes we use to mark time, from the cooling of your coffee to the burning of stars. Time, in this view, is not a river we float down. It is the current created by the universe's one-way slide from order into chaos. Our conscious experience of a flowing present could be a narrative constructed by our brains, a way to make sense of this irreversible thermodynamic drift. These ideas collectively suggest that the hidden architecture of reality may be a vast, timeless network of quantum connections. Our dimension of time is not a hidden direction to be discovered, but a collective phenomenon, a story that the universe tells itself as it moves from one correlation to the next, forever chasing a state of equilibrium it will never reach. The ticking clock is not measuring a fundamental dimension, it is recording the universe remembering itself, one irreversible change at a time. Yet if time itself is an emergent story, what about the very stage it unfolds upon? The dimensions of space may also be stories told at different scales. This is the startling implication of a concept called the spectral dimension, a way of measuring the true dimensionality of reality, not with a ruler, but by watching how something moves through it. Imagine releasing a single drop of ink into a still glass of water. In our familiar three-dimensional world, the ink will slowly diffuse outward, spreading in a characteristic cloud. The rate at which that cloud expands, how quickly it explores the volume available to it, tells you something fundamental about the space it is moving through. Now picture performing that same experiment, but instead of water, you drop the ink into a dense sponge, a tangled ball of yarn, or a flat sheet of paper. In each of these different structures, the ink would spread at a different rate because the effective dimensionality of the medium is different. The spectral dimension is precisely this, a measure of dimensionality deduced by observing how a random walker or a diffusing particle explores the fabric of spacetime itself. It asks a simple, profound question: how many directions are truly available for something to wander at a given scale? The answer, from several cutting-edge approaches to quantum gravity, is not what we expect. In frameworks like causal dynamical triangulations and loop quantum gravity, the spectral dimension is not a fixed number. It runs. At the large, everyday scales of planets and galaxies, the diffusion behaves exactly as if spacetime is four-dimensional, 3 of space and 1 of time. A particle explores the cosmos just as our ink drop explores the water, confirming the classical stage of general relativity. But as you theoretically probe smaller and smaller distances, approaching the violent turbulence of the Planck scale, something extraordinary happens. The spectral dimension begins to shrink. The rate of diffusion changes, indicating that the particle is exploring fewer effective directions. The mathematics suggests that at these extreme energies, the spectral dimension flows down toward a value of 2. This is a concrete mathematical result, not just a speculation. It implies that a particle wandering the ultra-microscopic foam of spacetime finds its paths constrained, as if the very concept of volume evaporates and the world becomes more like a surface. Think of walking through an open field versus pushing through a thick, tangled hedge. In the field, you can move freely in all directions. In the hedge, your motion is severely restricted, effectively reducing the dimensions you can travel. At the Planck scale, spacetime itself may become such a tangled quantum topological structure that its effective dimensionality collapses from 4 to 2. This provides powerful evidence that the number of dimensions is not a fundamental, unchanging constant of nature, written into the cosmos at its birth. Instead, dimensionality is a fluid property, a temperature-dependent phase of reality. The four-dimensional continuum we rely on is a low-energy phenomenon, a calm, classical limit that emerges from a more primitive, lower-dimensional quantum substrate when things cool down and spread out. The stage of our existence has a variable resolution, and what we perceive as its permanent depth is merely the view from a very particular, very peaceful vantage point in an otherwise wildly fluctuating quantum landscape. The fluidity of spacetime's dimensions reveals a stage that changes with our perspective. But what if the actors themselves, the particles and forces, also point to a simpler truth? In the complex world of particle physics, calculating how particles scatter and interact after a high-energy collision is a monumental task. For decades, these calculations required tracking every conceivable path a particle could take, a labyrinth of Feynman diagrams representing virtual particles popping in and out of existence, respecting the sacred principles of locality and unitarity. Locality means particles interact only at single points in spacetime, and influences travel no faster than light. Unitarity ensures probabilities always add up to 100%. These are the bedrock assumptions of our quantum field theories, the rules of the game. Yet in 2013, a team of physicists including Nima Arkani made a discovery that seemed to bypass these rules entirely. They found that the incredibly complex results of particle scattering calculations could be derived from the volume of a beautiful, multi-dimensional geometric shape called the amplituhedron. This object exists not in our familiar spacetime, but in an abstract mathematical space called the Grassmannian. The amplituhedron is a jewel-like polytope, a higher dimensional cousin of a polygon or a polyhedron, whose interior volume directly encodes the probability of a given scattering outcome. The revolutionary aspect is how it achieves this. To calculate a scattering amplitude using the amplituhedron, you do not sum over infinite paths of virtual particles. You do not explicitly enforce locality or unitarity. You simply calculate a geometric volume. The principles of locality and unitarity are not inputs to the calculation, they are outputs. They emerge automatically from the geometry of the shape itself. It is as if you were trying to predict the outcome of a game of pool. The traditional method requires simulating every possible bounce and spin of each ball on the table, a computationally nightmarish task. The amplituhedron approach is like discovering that the final arrangement of the balls is simply the shadow of a perfect, higher-dimensional shape, and by measuring that shape, you get the answer directly without simulating the chaos. This suggests something profound about the nature of reality. The properties we consider most fundamental, that things happen somewhere specific and that cause and effect are preserved, may not be primitive truths. They could be secondary phenomena, shadows cast by a deeper, more elegant geometric reality that operates in a mathematical space we cannot directly perceive. In this view, spacetime and its causal structure are not the foundation. They are the user interface, a simplified projection that emerges from the intricate, timeless geometry of shapes like the amplituhedron when we ask questions about particles and their interactions. The hidden dimensions of this framework are not curled-up spatial directions, but the abstract coordinates of a purer mathematical realm, where the answers to our most complex physical questions are waiting, not as probabilities but as volumes. The most mysterious force in the cosmos may be a whisper from another dimension. For over 2 decades, astronomers have known our universe is not just expanding, but its expansion is accelerating. Something is pushing space itself apart with ever-increasing speed. This something is labeled dark energy, a placeholder for a profound ignorance that makes up roughly 70% of the universe's total energy budget. It acts as a kind of anti-gravity, a persistent, uniform negative pressure embedded in the vacuum of space. But what if this force is not a property of our 3-dimensional world at all? What if it is a shadow, a cosmic side effect of our universe's position and motion within a higher dimensional reality? In the brane world scenarios we explored earlier, our universe is a 3-dimensional membrane adrift in a bulk with more dimensions. The equations governing such a brane are not static. As it floats and evolves in the bulk, its own geometry can be influenced by the larger space it inhabits. One compelling possibility is that the acceleration we measure is not driven by an exotic energy within our brain, but by the brain's own curvature as it responds to the bulk. Imagine a sheet of paper floating on the surface of a gently moving pond. As ripples pass beneath it, the paper itself will curve and warp. Now, if you were a tiny ant living entirely on that 2-dimensional sheet, you would not perceive the water or the ripples. You would only measure that your world was mysteriously stretching, that distances between points were increasing in a way you could not explain by anything on the sheet itself. For us, the ant's unexplained expansion is dark energy. In this view, the observed acceleration could be a geometric effect, a consequence of our brain's embedding and dynamics in the higher dimensional bulk. The mathematics shows that certain types of curvature induced from the bulk into our brain can mimic the effect of a cosmological constant, producing the exact kind of uniform, repulsive pressure we observe. Another, even more dramatic possibility involves the other actors in the bulk, other brains. Recall the cyclic model where our Big Bang was triggered by a collision with a parallel brane. In the long epochs between collisions, as the branes slowly move apart or oscillate in the bulk, their gravitational influence on one another can stretch the space within each brane. The gentle tug of a neighboring universe felt across a hidden dimension could be slowly inflating our own. This interaction would create an effective energy that permeates all of space, a cosmic tension in the membrane that manifests as a driving force for expansion. We would interpret this tension as dark energy, completely unaware that its source is a ghostly pull from a parallel reality just out of reach. This framework transforms dark energy from a mysterious substance into a relational phenomenon. It is not a thing, but a condition, a symptom of our universe's place in a grander architecture. the relentless acceleration becomes a clue, a faint signal that we are not alone in the bulk, and that the true dynamics of the cosmos are written in dimensions we have yet to fully comprehend. Dark energy's mysterious push hints at a universe shaped by unseen dimensions, but there is another interpretation that places the source of multiplicity not outside our world, but within its very quantum heart. Every moment, every decision, every quantum event presents a choice the universe refuses to make. In the traditional Copenhagen interpretation, a quantum system exists in a blur of possibilities until an observation forces it to pick one definite state, collapsing the wave function. But an alternative view proposed by Hugh Everett in the 1950s rejects this collapse entirely. In the many worlds interpretation, the wave function never collapses. It simply continues to evolve deterministically and unitarily according to the Schrödinger equation. So what happens when a measurement occurs when a particle faced with two paths seems to randomly choose one? According to Everett, it chooses both. The universe itself splits, or more accurately, different components of the universal wave function that were once coherently linked become separated or decohered. Each possible outcome becomes real in its own branch of reality. This is not science fiction, but a rigorous, if mind-bending, consequence of taking quantum mechanics at its most literal mathematical word. Imagine standing before a doorway with two rooms. In the Copenhagen view, you open the door and one room is randomly there, the other gone. In the many worlds view, you open the door and the universe divides like a hallway branching in two. In one branch, you walk into the left room. In the other, perfectly real branch, you walk into the right room. Both views are equally real, but from that moment forward, you are forever unaware of each other. The branches have decohered, their quantum phases scrambled so they can no longer interfere or communicate. This process is not a rare cosmic event. It is happening constantly at an unimaginable rate with every quantum fluctuation, every particle interaction, every neural firing in your brain. The universe is not a single timeline, but a perpetually blooming tree of forking paths, where every possibility mandated by quantum law is realized somewhere in the sprawling multiverse. Now consider the mathematical space that describes this totality, the configuration space of the universal wave function. This is an abstract realm of staggering dimensionality, where every single particle's position and property is a coordinate. Within this vast landscape, each decoherent branch of reality does not just represent a different story. It represents a movement in an effectively new direction. As the wave function evolves and branches, it is constantly exploring orthogonal trajectories in this space, trajectories that represent mutually exclusive histories. Each branch is like a new, hidden dimension of possibility being generated in real time. Think of it like a growing crystal. As it forms from a solution, it can grow in several possible directions. Each new facet that extends represents a new axis of growth, a new dimension added to its structure. In the same way as the universal wave function evolves, every decoherence event adds new, effectively independent directions to the tapestry of reality. These are not spatial dimensions you could travel, but dimensions in the space of possible worlds. In one of these dimensional directions, a coin you flipped landed heads. In an orthogonal direction, it landed tails. In another, a quantum event in a distant star took a different path a billion years ago, leading to a galaxy that never formed. The branching is ceaseless, weaving a multidimensional structure of what might be called the multiversal landscape. This reframes the nature of existence profoundly. We do not inhabit a universe with a fixed number of hidden spatial dimensions. Instead, we inhabit a single thread within a reality whose true form is a dynamic, ever-expanding dimensional manifold of alternate histories and futures. The hidden dimensions are not curled up or warped, they are the countless other versions of now, the roads not taken that are nevertheless being traveled. Our persistent sense of a single, definite reality may simply be the view from one solitary path on this infinite tree, forever unaware of the whispering branches growing in directions we cannot point to, but whose mathematical reality is etched into the fundamental wave function of everything. The branching multiverse of many worlds suggests a reality of staggering multiplicity, but one final hypothesis pushes this idea to its ultimate logical extreme. It proposes that the true nature of existence is not merely complex but fundamentally simple, because at its core there is nothing but mathematics itself. This is the mathematical universe hypothesis championed by physicist Max Tegmark. Its premise is as bold as it is elegant. Our physical reality is not just described by mathematics, which is the successful method of all science. Instead, it is a mathematical structure. In this view, the universe does not contain mathematical truths like circles or prime numbers. It is those truths embodied. Think of a perfect triangle. In our world, we can draw an approximation of one with pencil and paper. But the ideal triangle, with sides of perfect straightness and angles that sum to exactly 180 degrees, exists as an abstract, immutable concept in the realm of mathematics. Tegmark's hypothesis suggests that our cosmos is, in the same way, an instantiation of a specific, self-consistent mathematical object. The equations of general relativity that describe the curvature of spacetime, the wave functions of quantum mechanics that describe particles, the entire edifice of physical law, these are not just models of the universe. They are its blueprints, and the universe is the building constructed from them. The consequence of this is breathtaking in its scope. If a mathematical structure is self-consistent, free from internal contradictions, then according to this hypothesis, it exists physically somewhere in the ultimate ensemble of all realities. Every possible geometric shape, every conceivable set of equations, every variation on the rules of logic that does not lead to a paradox, manifests as a real physical universe. Our particular cosmos, with its 3 dimensions of space and 1 of time, governed by the specific constants and forces we have measured, is simply one mathematical object among an infinite plenitude. It is the particular solution to a specific set of differential equations that we happen to find ourselves within. This reframes the mystery of our universe's seemingly fine-tuned parameters. We do not live in a special universe, we live in one that is mathematically possible, and because we are self-aware structures within it, we necessarily observe the laws that allow for our own existence. This is known as the anthropic principle, applied to a landscape of mathematical structures rather than physical constants. In a cosmos that is literally mathematics, the concept of hidden dimensions takes on a new clarity. Dimensions are not physical directions that might be curled up. They are mathematical parameters, variables in the equations that define a given structure. Our universe is defined by a set of equations whose solutions naturally yield 4 large dimensions. But right next to ours in the vast library of mathematical possibility are structures whose defining equations yield 5 dimensions or 11 or 248. Some might have time that flows in 2 directions or where the very concept of number is different. These are not alternate physical universes in a branching multiverse, but entirely separate mathematical realities, each as real as our own, yet completely disconnected because they obey different foundational axioms. To grasp this, consider the world of a video game. The game world is at its heart a mathematical model running on computer hardware. Its laws are the rules of its programming. For a character inside that game, its world is utterly real, defined by its own internal logic. Our universe, in this view, is akin to that character's world, but where the computer is the abstract, Platonic realm of mathematics itself. There is no external hardware, no programmer, just the inexorable existence of all consistent structures. This hypothesis dissolves the final boundary between the map and the territory. The mathematics is not a description of reality, it is the reality. And in that infinite, silent library of mathematical forms, every possible dimension, every conceivable geometry, every universe that can be written down without contradiction, is not just a thought but a place. Our deepest mystery may not be out in the cosmos, but within the very experience of being. You are listening to this voice, perceiving colors, feeling the weight of your own existence. This inner world of subjective experience, what philosophers call qualia, presents the hard problem of consciousness. Why should the intricate electrical and chemical ballet of a brain produce the vivid, private movie of self-awareness? Physical science maps the objective machinery, but it struggles to explain the subjective viewer. Some thinkers propose that the solution lies not in finding a new particle within the brain, but in expanding our map of reality to include dimensions beyond the physical. This is not a mystical claim, but a serious interdisciplinary hypothesis. Integrated information theory, developed by neuroscientist Giulio Tononi, offers a mathematical approach. It proposes that consciousness corresponds to a system's capacity for integrated information, denoted by the Greek letter phi. A system with high phi, like a human brain, has a vast repertoire of differentiated states that are also unified, meaning you cannot split the experience into independent parts without losing something essential. The theory suggests that this integrated information exists in a kind of abstract space, a phenomenal space with its own axes and dimensions. These dimensions would not be spatial in the conventional sense. They would represent degrees of freedom for experience itself, axes for color, sound, emotion, and thought, all woven into a single, unified fabric of feeling. In this view, your mind is not generating consciousness. It is a receiver, or a complex structure that allows this higher dimensional phenomenal space to express itself through the specific architecture of the brain. The brain's neural networks, with their trillions of connections, create a shape, a complex informational geometry that matches a particular region within this space of all possible conscious states. When you see the color red, it is not just a wavelength of light triggering a neural pattern. It is the brain's network accessing a specific coordinate, a unique point in the dimensional landscape of qualia. This idea finds a strange echo in philosophical idealism, a view that turns materialism on its head. Idealism suggests that consciousness is not a product of the physical world, but the fundamental ground of all existence. The physical universe of space-time and matter is what consciousness looks like from the outside, a shared representation or a consistent dream. From this perspective, the dimensions of physics, the three of space and one of time, are not the primary reality. They are the stable, collective framework that emerges within a deeper, more fundamental conscious field. The hidden dimensions, then, might not be spatial dimensions curled up at the Planck scale, but the very dimensions of experience from which the physical world condenses. The hard problem dissolves because there is no longer a need to explain how matter creates mind. Instead, mind is the canvas and matter is the painting. The laws of physics become the consistent rules of this shared conscious experience, much like the rules of perspective govern a painting to create a coherent three-dimensional illusion on a two-dimensional canvas. These are, of course, highly speculative frontiers where science meets philosophy. They are not proven theories, but they are serious attempts to grapple with the most intimate datum of our existence, our own awareness. They suggest that the final frontier in our search for hidden dimensions may not be at the edge of the cosmos or the heart of an atom, but in the quiet, undeniable fact of your own perception, a hint that the universe is not just stranger than we imagine, but perhaps more deeply connected to the observer than we have ever dared to suppose. The holographic principle paints a picture where our reality is a projection, but how does that projection maintain its stunning coherence? The answer may lie in the universe's most reliable secret keeper, quantum entanglement, and a discovery that reimagines spacetime as a cosmic error-correcting code. The AD-SCFT correspondence, a precise mathematical duality, is the key that unlocked this insight. It shows that a theory of gravity operating in a higher dimensional, curved bulk space is perfectly equivalent to a quantum field theory living on its lower dimensional boundary, a hologram without gravity. For years, this was a breathtaking mathematical equivalence, but its deeper meaning was elusive. Recent breakthroughs have revealed that the equivalence is not just a map, it is a blueprint for how the higher dimensional world is constructed. The geometry of the bulk, the very distance between points and the smooth curvature of space, is not fundamental. It is built thread by thread from the entanglement patterns of the quantum particles on the boundary. Where there is a high degree of entanglement between boundary regions, the corresponding points in the bulk are close together, connected by short geometric pathways. Where entanglement is weak or absent, the bulk points are far apart. Spacetime is quite literally woven from quantum connections. This turns our intuition inside out. An object moving smoothly through the three-dimensional bulk is not taking a simple local journey. From the perspective of the two-dimensional boundary, that motion is represented by a fantastically complex, non-local rearrangement of quantum information across the entire holographic surface. A single step in the higher dimensional world corresponds to a coordinated change in millions of entangled relationships on the boundary. This is where the concept of quantum error correction enters the story, and it is a revelation. In our everyday computers, error-correcting codes protect digital information by adding redundancy, like sending a message 3 times to ensure it gets through despite static on the line. Quantum information is infinitely more fragile, and protecting it requires profoundly clever codes that store a single logical qubit of information across many physical qubits in a highly entangled state. The remarkable discovery is that the add-SCFT correspondence itself behaves exactly like one of these quantum error-correcting codes. The higher dimensional bulk space is not a given, it is the protected logical information. The lower dimensional boundary is the physical, noisy system where the data is actually stored in a redundant, entangled form. Local disturbances in the bulk, like a small asteroid or a stray photon, correspond to errors that affect only a few of the boundary qubits. Because the information is spread out holographically across the entire entangled network, those local errors can be detected and corrected without losing the essential data. The geometry of the bulk emerges because this specific pattern of entanglement on the boundary is the one that best protects quantum information from corruption. Think of a cherished family story passed down through generations. No single person holds the complete, perfect version. Instead, the story is spread across the memories of every family member, each with slightly different details and perspectives. By comparing all these individual accounts, the true, coherent narrative can be reconstructed, even if some details are misremembered or lost by a few. The higher dimensional bulk is that true, reconstructed narrative. The boundary is the collective, slightly imperfect memories of every family member. The process of comparing and reconciling those memories, the error correction, is what builds the feeling of a solid, continuous history. In this cosmic code, the hidden dimensional geometry is not just a place, it is a protective mechanism. The reason our universe appears to have a stable, three-dimensional structure may be because that particular geometry is an exceptionally good quantum error-correcting code, one that preserves the integrity of information against the constant background noise of quantum fluctuations. The fabric of reality is not just connected, it is fault-tolerant, with every point in space serving as a backup for every other, all linked through an invisible web of entanglement that keeps the cosmic story from falling apart. The universe remembers the past but not the future. This is the arrow of time, the most familiar yet profound asymmetry in all of existence. Eggs scramble but never unscramble. Ice cubes melt in your drink but never spontaneously reform from the water, and we grow older, never younger. These are not just quirks of our local environment. They are universal expressions of the second law of thermodynamics, which states that entropy or disorder always increases in an isolated system. This law gives time its irreversible direction, its relentless arrow. Yet this presents a deep puzzle. The laws of physics themselves, from Newton's mechanics to Einstein's relativity to quantum electrodynamics, are almost entirely time-symmetric. They work just as well if you run the film of the universe backward. So where does the arrow come from? The answer appears to lie not in the laws, but in a single, extraordinary starting condition. Our universe began in a state of exceptionally low entropy. The Big Bang was not a chaotic explosion, but an event of stunning uniformity and order. Picture a brand new deck of cards perfectly sorted by suit and value. That deck has very low entropy. Shuffle it once and the entropy increases. Shuffle it 1,000 times and it becomes a random, high-entropy mess. The universe started as that perfectly sorted deck. All the matter and energy were packed into an incredibly hot, dense, but remarkably smooth and uniform state. From that pristine starting point, the only way to go was toward higher entropy, toward greater disorder. As the universe expanded and cooled, that initial smoothness clumped into galaxies, stars, and planets, all while the overall entropy of the cosmos steadily increased. The arrow of time is not built into the engine of physics. It is a consequence of the fuel we started with. We remember the past because the past had lower entropy. The future will have higher entropy. Our entire experience of cause and effect, of memory and aging, is swept along in this one-way cosmic slide from order to chaos. But this explanation only deepens the mystery. Why did the universe begin in such an improbably ordered state? Why was the entropy so low to begin with? One radical possibility emerges when we place our universe within the hidden dimensional landscapes we have explored. Perhaps our observable cosmos, with its clear arrow of time, is not the whole story. It could be a local fluctuation, a rare eddy of low entropy within a vastly larger, higher dimensional structure where entropy is overall at its maximum. Imagine an infinite, calm ocean that has existed forever, a state of maximum disorder and thermodynamic equilibrium. In such an eternal, high-dimensional multiverse, absolutely nothing happens on average. But within that sterile equilibrium, tiny statistical fluctuations are inevitable. Very, very rarely, by pure chance, a random patch of this eternal bulk will momentarily fluctuate into a state of lower entropy. Our Big Bang could be exactly that, a random, localized dip in entropy within an otherwise featureless, timeless sea. In this view, our entire cosmic history, from the first second to the last fading star, is just the universe relaxing back toward that high-entropy equilibrium. The arrow of time we experience is not a fundamental feature of all reality. It is a temporary, local phenomenon, the sigh of a small region as it returns to the silent, disordered norm of a larger multiverse. Our perception of a flowing present, of a definite past and an open future, is then a side effect of our position within this specific fluctuation. We are riding the wave of entropy increase from a rare low point back to the featureless high-dimensional ocean. This connects the most intimate feeling of time's passage to the grandest architectures of reality. The direction of time may be a clue that we are living in a bubble within something much larger and stranger, a hidden dimensional landscape where our entire dramatic history is just a brief, beautiful anomaly in an eternal, quiet expanse. Theoretical landscapes are breathtaking, but they remain maps until we find the territory. The true test of hidden dimensions lies not in equations, but in evidence, in the hard, empirical data we can gather from our corner of the cosmos. Physicists are not waiting passively for answers. They are actively hunting, deploying ingenious experiments that probe the very edges of reality, searching for the faintest tremors that might betray a world beyond our own. One of the most direct searches unfolds within the world's most powerful microscopes, particle colliders like the Large Hadron Collider. Here, scientists smash protons together at velocities nearing the speed of light, recreating the searing energies of the early universe. In these fleeting billion-degree collisions, they are looking for a very specific kind of silence, missing energy. According to our standard three-dimensional laws, energy and momentum must be perfectly conserved in every collision. Every fragment, every new particle created must account for the total energy of the collision. But in models with large extra dimensions, a new escape route exists. If enough energy is concentrated in the collision, it could theoretically create a graviton, the particle that carries gravity. Unlike every other particle tied to our three-dimensional brane, the graviton could promptly vanish into the extra dimension, carrying its energy and momentum away with it. In the detector, this would appear as a glaring imbalance, a collision where a significant amount of energy simply disappears, leaving no trace. It would be as if you rolled two billiard balls together with tremendous force, and they simply stopped dead with no sound, no heat, no fragments flying away, because the energy of the impact had vanished into a hidden room adjacent to the pool table. While no definitive missing energy signal has been found yet, the relentless search continues, tightening the constraints on how large and how accessible these extra dimensions might be. A second, exquisitely delicate frontier operates on a tabletop scale, probing the force of gravity itself at distances smaller than a millimeter. Newton's law of universal gravitation, which says the force weakens with the square of the distance, is a law for a three-dimensional world. If one or more extra dimensions are large enough, gravity's behavior should change at very short ranges. At scales smaller than the size of the extra dimension, gravity would begin to spread into that new volume, causing its strength to diminish more rapidly. To test this, physicists have built devices of astonishing sensitivity. They use tiny, suspended mirrors or oscillating cantilevers, often cooled to near absolute zero to eliminate thermal noise, to measure the gravitational attraction between minuscule masses separated by mere microns. They are essentially trying to weigh a grain of sand with a scale so precise it could detect a virus landing on it. By mapping the gravitational force at these microscopic distances, they are drawing a detailed map of gravity's behavior, looking for any deviation from Newton's inverse square law that would signal gravity leaking into an unseen realm. So far, gravity has obeyed the classical law down to about 50 microns, but the search presses onward into ever smaller gaps. The third great observatory is the cosmos itself. Astrophysicists scrutinize the largest structures and the oldest light for anomalies that might hint at higher dimensional physics. Could the mysterious acceleration of the universe's expansion, driven by dark energy, be a subtle effect of our brane's curvature or its interaction with other branes in the bulk? Are there strange signatures in the cosmic microwave background, the afterglow of the Big Bang, that could be imprints from a pre-Big Bang phase in a cyclic model? Even the behavior of black holes and the way they evaporate via Hawking radiation could provide clues, as their thermodynamics is deeply connected to holographic principles and information theory. Each of these experimental paths, from the ultra-high energy to the ultra-precise to the astronomically vast, represents a different way of asking the same fundamental question. Is our three-dimensional stage the full reality, or merely the visible part of a deeper, richer structure? The experiments are difficult, the signals expected to be faint, but the pursuit continues because the potential discovery is monumental. It would not just add a new chapter to physics, it would rewrite the entire book of reality, revealing that the universe has been whispering its secrets in dimensions we are only now learning how to listen for. The journey through these 30 visions of reality reveals a single, unifying truth. Our most profound scientific and philosophical quests inevitably push us to look beyond the world as it appears. Whether through the curled-up geometry of Calabi-Yau manifolds, the warped landscapes of brane worlds, or the abstract codes of quantum information, each theory is a testament to human curiosity, insisting there must be more to the story. The rigorous mathematics of string theory, the philosophical breadth of the simulation hypothesis, and the speculative elegance of emergent spacetime may seem worlds apart, yet they are all responses to the same deep cosmic whispers, the anomalies and mysteries that our standard model of reality cannot explain. They collectively paint a portrait of a universe that is not simply larger than we imagined, but constructed in a manner far stranger and more wonderfully layered. This investigation into hidden dimensions transcends a niche puzzle in theoretical physics. It becomes a fundamental inquiry into the nature of physical law itself, asking whether our constants and forces are absolute or merely local bylaws. It probes the relationship between information and existence, questioning if the solidity of matter and the flow of time are primary realities or magnificent secondary effects emerging from a more primitive substrate. The search forces us to confront what it means for something to be real, challenging the primacy of our senses and inviting us to trust in the power of mathematics and logic as guides to truths we may never directly see. While many of these ideas remain beyond our current ability to test, the frontier is not static. The next generation of particle colliders, ever more sensitive tabletop gravity experiments, and space telescopes peering back to the first light of the cosmos are actively gathering data that could at any moment reveal a crack in our three-dimensional facade. A single anomaly in the way gravity behaves at a microscopic distance, or a pattern of missing energy in a high-energy collision, could be the first hard evidence that we are not alone in the bulk, that our universe is a membrane adrift in a higher dimensional sea. Theoretical breakthroughs in understanding quantum gravity or decoding the holographic principle may similarly provide the conceptual key to finally unifying the very large and the very small. The veil over reality's full architecture may be lifting in our lifetime. As you reflect on this exploration, which of these 30 theories resonates most deeply with your own intuition about the cosmos? Was it the cosmic hologram, the infinite branching of many worlds, or the timeless geometry of a single mathematical structure? Share your thoughts in the comments below, and let us continue the conversation about the most compelling hidden dimensions of existence.